This is Chapter 5 of the Electric Power Distribution course. It covers power distribution cables. In this chapter, I will cover the following topics. I will start describing the main types of power cables. Then, I will discuss the cable selection criteria. Then, I will present the short circuit current calculation. And finally, I will describe the cable risers and trays. This chapter will be covered in 2 lectures. This is the first one. So, I will start presenting the main types of power cables and their classifications. In general, power cables are classified based on their voltage levels, which are low, medium, high, or extra high voltage levels. Their type of insulation material used around the conductors. The conductor material, such as copper and aluminum. And the conductor construction and layout. So, power cables are usually classified according to their operating voltage as follows. Low voltage cables, up to 1 kV. Medium voltage cables, from 3 kV up to 30 kV. And high voltage cables, more than 30 kV. There are other classes for higher voltage levels, but since we are concerned with distribution cables, these are the most related classes. For same cross-sectional area, single-core cables' ampacity is greater than that of multi-core cables. This is due to the fact that currents in different conductors interfere with each other. And heat dissipation in a single core is more effective than in multi-core cables. Disadvantages of 3-core cables are, that individually the cables are larger and heavier than a single core cable, which limits the length of the cable that can be installed on one drum, before it exceeds vehicle height and weight. Manufacturers also have a limit on their drum twisting capabilities to lay up 3-core cables. The maximum conductor size of 3-core cables is thus lower than single-core counterparts, requiring more joint bays on a long route. 3-core cable joints are more complex than single-core joints. Thus you would find that for small conductor installations, 3-core cables were used, and for large conductor installations single-core cables were used. But from economics point of view, multi-core cables are preferred. Thus, for low current short length requirements, for instance in industry, 3-core cables are better, whereas for high power circuits, for instance in transmission, single-core installations are more cost-effective. The next classification is based on conductor conductivity and its material type. We distinguish mainly 2 types, copper and aluminum. For instance, copper is used with low voltage for minimum voltage drop, because it has lower resistivity and higher conductivity than aluminum. While aluminum is used with medium and high voltage, for smaller current ampacity, and thus fewer voltage drop. The next classification is based on conductor construction and layout. Beyond choosing between aluminum or copper, the wiring expert will understand the difference between stranded and solid wire, and will choose the appropriate wire core to use for their chosen project. While solid wire consists of a single metal core, a stranded wire is composed of numerous thinner wires twisted together into a cohesive bunch. Both types of wire are appropriate for commercial and residential installation, however each has particular advantages and disadvantages that lead to the choice of one over another, for each particular application. The next classification is based on their type of conductor primary insulation. We distinguish mainly 2 types. The cross-linked polyethylene cables, also called XLPE cables. And the polyvinyl chloride cables, also called PVC cables. The XLPE cables are used with medium voltages and sometimes low voltages, but are very expensive. Therefore, they are more preferable in medium voltage applications. Also, XLPE cables tolerate higher current than PVC cables. And they also withstand higher temperature, which can reach up to 90 degrees Celsius. Thus, their current carrying capability is higher than that of PVC. Hence, XLPE cables have higher short circuit capability than PVC cables. On the other hand, PVC cables are more popular in low voltage applications. They are used in most of buildings' electric wiring installations. They have lower cost than XLPE cables, but less current capacity. They are more resistant to water, oil, alkalis, and doesn't burn easy, thus requires less replacement. They have high melting temperature. At high temperature, higher than 80 degrees Celsius, it turns into soft material. Thus, PVC cables can be used with temperatures not exceeding than 70 degrees Celsius. This YouTube movie describes how the cables are manufactured. This movie can be accessed directly through the link shown below.
Much of today's high-tech equipment requires specialty wires and cables. From stage lighting to medical devices to robotics, wires and cables have to be custom designed and expertly manufactured to perform in a specific way and withstand various environmental conditions. Cables can be designed to withstand high temperatures or perform special functions such as sensing pH levels or proximity to objects. At the heart of a cable are electrical wires, called conductors. A conductor begins as a bare copper wire. This extrusion machine coats it in plastic. Chilled water solidifies the plastic around the wire as insulation. This isolates each wire from its neighbors. Every conductor passes through a machine called a spark tester. It runs current through the conductor to ensure the insulation is flawless. If there's even the smallest break in the insulation, the machine will sound the alarm and locate the spot. The conductor then enters a machine called a cabler. It unrolls spools of insulated conductors and unites them with other components to form the cable's inner workings. At the center of this particular cable is a twisted pair of insulated conductors. Around them go color-coded insulated conductors and fillers to fill in the gaps between the conductors, giving the cable a smooth cylindrical shape. Here, the fillers are strands of polypropylene foam. An orientation plate aligns the components in the proper configuration as they enter the cable assembly die. The components exit the die with the fillers wound around the insulated conductors, which wrap around the central wire. The next machine, called a taping head, wraps binder tape around the cable. This tape holds everything tightly in position so that the assembled components don't unravel. This is a different type of cable assembly machine. Like before, all the insulated conductors unroll from their reels and travel through the holes of an orientation plate. Dies divide the 6 conductors of this cable into 3 groups of 2, twisting the conductors of each pair together. The machine then wraps each twisted pair in a shield made of aluminum-coated polyester. Shielding eliminates what's known as crosstalk, signals interfering with each other. The next die joins additional wires that don't need to be shielded to the shielded ones. Then everything gets twisted into one cable. Then a final twisting, seen here in slow motion. The actual speed is 1,000 revolutions per minute. The next machine wraps tissue paper around the cable. Then an extruder applies a jacket made of a plastic and rubber compound. The tissue paper acts as a separator, preventing the jacket from sticking to the cable inside. Sometimes, instead of tissue paper, the cable runs through a bath of talc. Talc is a mineral that absorbs heat, So, just like tissue paper, it prevents the jacket from sticking. Once again, as the cable exits the extruder, chilled water solidifies the molten material into a jacket. A wheel with raised lettering imprints the manufacturer's name and technical specifications into the jacket. Certain jacketed cables need a braided shield to eliminate electrical interference. This machine has 48 carrier spools, each of which holds 10 wires made of tin-plated copper. As the jacketed cable moves upward through the machine, the spools move in a programmed pattern, weaving the shield around the cable. From there, a last trip through the extruder for a final thermoplastic jacket. And the custom-made cable is ready to be connected and powered up.
Next, I will present the main criteria for selecting power distribution cables. For instance, how to select a solid or a stranded wire type. While both types of wire will transmit electricity effectively, each is better suited to specific applications, in both residential and commercial uses. Solid wire is the wire of choice for outdoor or rugged duty applications, which may expose the wire to corrosive elements, or adverse weather condition. The main advantages of solid wire are cost, simplicity, and durability. The stranded wire, conversely, serves a better purpose in intricate usages, such as electronic devices and circuit boards, where the wire will be protected but may undergo bending or twisting, in order to connect electric and electronic components. So, the advantages of stranded wires are their malleability and flexibility. Cable sizes are selected based on the following characteristics. Cable ampacity, or capacity. It is the maximum current carried by the cable. It depends on several factors such as burial depth, environment, air or cable tray distribution, soil temperature, grouping, etc. So, this maximum current must be calculated using derating factors. Voltage drop allowance is the second characteristic. It is very critical in low voltage distribution networks. The third main characteristic for cable selection is the short circuit withstand capabilities. It is the short circuit current versus time relation. We need to check if the selected cable will withstand the expected short circuit current at fault, for the given time duration or not, and if the circuit breakers will operate before the cable failure. Recall this design cycle flowchart that I presented during the course introduction. The cable selection criteria is highlighted in orange color. There are mainly 4 steps to follow, in order to finalize the cable selection. The first 3 are covered in this chapter, but the 4th one will be covered more after the chapter about power distribution system protection. So, there are mainly 3 steps to follow, during the selection of the power distribution cable, for a specific feeder. Step 1, is the first cable selection. First, we determine the allowable current I, in the circuit, which will guide the choice of the cross-section area of the cable. Second, we determine the derating factors, K factor, based on how the cable will be installed and laid out. Third, we get the modified current value I prime, which is determined as current I divided by derating factor K, and this value determines the cable ampacity. And fourth, we select a cable cross-section area based on the new current value I prime. Step 2, in this step, we need to perform a voltage drop calculation, either manually or using load moment and chart techniques. And finally step 3, in this step, we perform the short circuit current check. We shall make sure that our selected cable can withstand short circuit currents, for a certain time interval, until selected protection responds. Let's see, through examples, how we can determine the cable ampacity, taking into account the derating factor. For instance, for underground cables, the effect of the ground temperature on the cable ampacity is given by the ground temperature derating factor in this table. This table gives examples of the derating factors for both PVC and XLPE cables as a function of the ground temperature. This table shows examples of derating factor for PVC and XLPE overhead cables as a function of air temperature. For underground cables, the burial depth derating factor is also used for the calculation of the final cable ampacity. Underground cables' burial depths depend on the voltage level. This table shows the typical depth ranges of the buried cables as a function of the voltage categories. For instance, low voltage cables are buried at a depth between 50 to 80 centimeters, while medium voltage cables are buried deeper at depths ranging between 80 centimeter and 1 meter. This table shows the derating factor based on burial depths for different conductor cross-section areas. Notice that, the deeper the cable is buried, the smaller is the derating factor, which means that the resulting final ampacity, based on which the cable should be selected, should be increased. This table shows examples of derating factor based on soil thermal resistivity. And this table shows examples of derating factors based on PVC rated temperature. In practice, we need to determine the individual derating factors based on different influencing parameters, as shown in the previous example tables. Then the resultant total equivalent derating factor is calculated as the product of all these factors. The total ampacity I', that is used for selecting the cable, is then calculated as the ratio of the maximum current demand divided by the total equivalent derating factor. The next step is the voltage drop calculation and checking if it is within the accepted limit. Usually, voltage drop in low voltage distribution systems must not exceed a total of 8% the nominal voltage. This 8% is the result of accumulated voltage drops in different elements of the system. For instance, voltage drop in the transformer is around 1%. And voltage drop from distribution transformer to main distribution panel board is about 3%. And voltage drop in the riser and trays is between 1 and 1.5%. And the voltage drop in the remaining elements, until the point of connection of the load, should not exceed 2.5%. The Qatari standard, adopted by Karema, limits the voltage drop on the 11 kV system to 5%. But allowing it to reach 7% in rural areas with extended overhead lines. Let's practice on one example and calculate the voltage drop using the Siemens given chart of percent voltage drop on 220/380 volts supply, with power factor equals 0.9, and conductor temperature of 50 degrees Celsius. In this chart, the percent voltage drop lines are plotted as a function of the load moment and conductor cross-section areas. The left side vertical axis is for the copper conductors, while the right side vertical axis is for the aluminum conductors. This chart was built using the load moment equation of the per unit voltage drop calculation. Let's suppose that we have selected initially the 70 mm² copper cable. And the load moment is 20,000 kVA meter. Then, at the point of intersection of the horizontal and vertical lines, we can find that the equivalent voltage drop in this cable is 5%. If we select a 70 mm² aluminum cable, then, the equivalent voltage drop in this cable will be 7%. Next, let's discuss the methods for short circuit current calculation. During a short circuit, a high amount of current can flow through a cable for a short time. This surge in the current flow causes a temperature rise within the cable. High temperatures can trigger unwanted reactions in the cable insulation, sheath materials, and other components, which can prematurely degrade the condition of the cable and may ignite fires. As the cross-sectional area of the cable increases, it can dissipate higher fault currents for a given temperature rise. Therefore, cables should be sized to withstand the largest short circuit that it is expected to see during a specific period of time. Short circuit could be symmetrical, such as in three-phase fault, or unsymmetrical, such as two-phase fault, two-phase to earth fault, or single-phase to earth fault. Note that, most occurred ones is the single-phase to earth, and symmetrical three-phase fault, which is the most severe. To deal with unsymmetrical faults, we use the symmetrical component analysis. For the three-phase symmetrical fault, the fault calculation is made on assumption of three-phase balanced system. The calculation is made for one phase only, as the current and voltage conditions are same in all three phases. When actual faults occur in electrical power system, such as phase to earth fault, phase to phase fault and double phase to earth fault, the system becomes unbalanced. This means that the conditions of voltages and currents in all phases are no longer symmetrical. Such faults are solved by symmetrical component analysis. Generally, single three-phase unbalanced vectors diagram may be replaced by three sets of balanced vectors. First one has positive phase rotation. Second one has opposite or negative phase rotation. Last one is cophasal. That means these vector sets are described as negative sequence, positive sequence, and zero sequence, respectively. The equations relating phase and sequence quantities are expressed as follows. Here are the phase voltage expressions, where A is a 120 degrees phase shifting vector. Therefore, line voltages can be expressed as shown here. Similarly, a set of equations can be written for sequence currents also. From these voltage and current equations, one can easily determine the sequence impedance of the system. The development of symmetrical component analysis depends upon the fact that in balanced system of impedance, sequence currents can give rise only to voltage drops of the same sequence. Once the sequence networks are available, these can be converted to single equivalent impedance, which can be used to solve the short circuit current. Let us consider Z1, Z2, and Z0 as the impedance of the system to the flow of positive, negative and zero sequence currents, respectively. For single phase to earth fault, the sequence currents are all equal, and are determined by this equation. For phase to phase faults, the sequence currents are determined using these equations. For double phase to earth faults, the sequence currents are determined using these equations. And for three-phase faults, the sequence currents are determined using these equations. Note that the three-phase fault is usually considered the most severe and gives maximum short circuit current. However, in case of interest in knowing the short circuit current for any of the faults, the corresponding fault equations can be used were shown in this slide. Now, I will present the method of calculating the minimum cable size, due to short circuit temperature rise. The minimum cable size due to short circuit temperature rise, is typically calculated with an equation of the form, where ISC is the prospective short circuit current, in amperes. A is the minimum cross-sectional area of cable conductor, in millimeters square. T is the duration of the short circuit, time to trip, in seconds. And K is the cable short circuit factor, or short circuit temperature rise constant. Note that the term, squared short circuit current ISC, multiplied by time t, is equivalent to the short circuit energy. The cable temperature rise constant K, is calculated based on the material properties of the conductor, and the initial and final conductor temperatures. Different international standards have different treatments of this temperature rise constant. As an example, the IEC 60364-5-54 standard suggests to calculate it as follows. For copper conductors, we can use this equation, where theta I and theta F are the initial and final conductor temperatures, in degrees Celsius, respectively. And for aluminum conductors, we can use this equation. Initial and final conductor temperatures are selected as follows. The initial conductor temperature is typically chosen to be the maximum normal operating temperature of the cable. And the final conductor temperature is typically chosen to be the limiting temperature of the insulation. In general, the cable's insulation will determine the maximum operating and limiting temperatures. As a rough guide, the following temperatures are common for the different insulation materials. Notice that, as mentioned earlier, the PVC has lower maximum temperatures than XLPE. The short circuit energy is normally chosen as the maximum short circuit that the cable could potentially experience. However, for circuits with current limiting devices, such as HRC fuses, then the short circuit energy chosen should be the maximum perspective let-through energy of the protective device, which can be found from manufacturer data. This table shows an example of tables that are provided by cables manufacturers. This is an example of kiloamps short circuit current for copper conductors which are PVC insulated. For instance, if we select a cable with a cross-section area of 150 mm², and would like to check the maximum short circuit current for a duration of 0.5 seconds, then we can obtain a value of 24.4 kiloamperes. Let's consider a practical example. In this example, we will size a cable for a 415 volts, line-to-line RMS, 37 kilowatts three-phase motor, from the motor control center to the field. We want to find what is the minimum size of the cable based on short circuit temperature rise. The following data was collected for the cable to be sized. Cable type, copper PVC/GSWB/PVC, 3 cores plus earth, 0.6/1 kV. Operating temperature, 70 degrees Celsius. Cable installation is done above ground, on cable ladder, bunched together with 3 other cables on a single layer, and at 30 degrees Celsius ambient air temperature. Cable run is 90 meters, including tails. Motor load is 37 kilowatts, under 415 volts 3-phase, full load current equals 61 amps, and power factor equals 0.85 lagging. Protection type is AMP-fuse, of rating equals 80A, max perspective fault energy I2T equals 90 kiloamp seconds, and 5 seconds melt time equals 550 amps. Step 1, we start with cable selection based on current rating, or ampacity. Based on the given data on the cable, we can start by determining the individual derating factors and then calculate the total equivalent derating factor. We can start with the air temperature derating factor since we were told that the cable is laid on a tray in the air. For that, we can use the Doha Cables catalog, and search for the corresponding air temperature derating factor. We know that the cable is PVC insulated and that the air temperature is 30 degrees Celsius. Then the corresponding derating factor is 1.15. The derating factor for groups of more than one multi-core cable in air can be determined from this table, which is also provided by the same cable manufacturer. In our case, the cable is laid with 3 other cables, which makes a total of 4 cables laid on a single tray. So, the derating factor for groups of 4 cables on a single layer is 0.79. The overall derating factor is therefore 1.15 times 0.79, that equals 0.9085. The cable minimum ampacity is therefore calculated as follows. The obtained value of 65.4 amps is the value that will be used to select the cable based on its ampacity. Given that the calculated derated current is 65.4 amps, then a first choice will be the followings. For cables laid in free air, according to Doha Cables catalog, the possible cable current ratings are given in this column. Among these values, the closest one equal or higher than the given rated current of 65.4 amperes, is 72 amperes. Thus, the 16 mm² cable is selected based on its ampacity, that satisfies the maximum current demand. In step 2, cable selection is checked based on voltage drop calculation. Suppose the 16 mm² cable is selected. If the maximum permissible voltage drop is 5%, is the cable suitable for a run length of 90 meters? A 16 mm² cable has an AC resistance of 1.39 ohms per kilometer, and a negligible AC reactance. The voltage drop across the cable is calculated as follows. So, the percent voltage drop obtained is 3.96%, which is lower than the maximum permissible voltage drop of 5%. Therefore, based on voltage drop considerations, the selected cable is suitable for the motor. In step 3, we need to check the permissible short circuit temperature rise. The cable is operating normally at 70 degrees Celsius and has a prospective fault capacity of 90,000 amperes square second. We know that PVC has a limiting temperature of 160 degrees Celsius. Using the IEC formula, the short circuit temperature rise constant for copper can be calculated, and is found equal to 115. The calculated minimum cable size, due to short circuit temperature rise, is therefore 2.6 mm². Therefore, our selected 16 mm² cable is still suitable for this application. Moreover, if we check with the cable manufacturer catalog, we can verify that the selected 16 mm² cable can withstand 800 amps, for a duration of 5 seconds, which is suitable since the selected fuse will melt at 5 seconds, for less current of 550 amps. This is the end of this lecture. I hope that it was clear and informative. Thank you for watching.